why? Because it happened and I couldn't tell you that it happened.
Oh, I can tell you it happened. I just can't tell you why.
That's
There's a
it.
difference.
It versus what?
Name the functional group. What do you have? Ester. Be more specific. Hydroxyl.
Hydroxyl, methyl ester.
Be more specific.
Benzaldehyde.
There is not a benzaldehyde in there. There is also no aldehyde. Although, are you thinking about the precursors?
Oh, yeah.
Because then you're spot on.
Okay.
This is not an enolate. For context, an enol is when you have an alcohol to an alkene. An enolate is the conjugate base of that, which actually has two resonance forms, a more stable and a more reactive resonance form. So we generally form enols by having a carbonyl deprotonating the alpha carbon, having resonance to the enolate, and then protonating that enolate. But in terms of equilibrium, the ketone is favored, not the enol. So no enol here, no enolate. There is an ester, there is an alcohol, a hydroxy group. Can we be more specific about the relationship between those two groups? Because that will tell us what type of reaction is happening here.
One of the ester, one of the alpha carbons is taken up, or one of the spots where it would be is taken up, so it has to be on one side. And there is a hydroxide in the beta position.
Okay, I missed what you said in the beginning. I'm sorry.
There's only one alpha hydrogen.
There's only one alpha hydrogen. Is there anything wrong with there only being one alpha hydrogen? Because we've actually seen 3, 2, 1, and 0 alpha hydrogens. So, but the second part that you said was what I want you to clarify. The position of the alcohol relative to the ester. Say it all at once.
Beta hydroxy carbonyl.
Good. This is a beta hydroxy carbonyl. Now, can you look back at your notes and tell me what type of reaction forms a beta hydroxy carbonyl? Nope.
Beta keto.
Claisen condensation is a beta keto ester, or more generically, a beta acyl carbonyl. Aldol addition gives us beta hydroxy carbonyls. So far, we have only seen aldol addition with aldehydes, ketones with ketones, or aldehydes with ketones. This gives us an ester. So this is what, there's no good name for these. I haven't seen a textbook, I haven't seen an online resource that names this combination specifically. So on the top of this sheet, you'll notice that I titled this Crossed Condensations. We talked about the Claisen condensation, ester to ester. We talked about the Deichmann condensation, intramolecular Claisen. These are what I'm calling other crossed condensations. Somebody asked this question last class. I forget who. The question was, what does crossed aldol condensation mean and what does crossed Claisen condensation mean? It's not somebody's name, which is actually a good thing to guess. It just means that you have two different carbonyl species. So you are crossing reagents. Aldol would be ideally like just the same things. Claisen would be just the same esters. Crossed is when you're mixing two different carbonyls. So these other crossed condensations might look aldol, might look Claisen, might give us beta hydroxy carbonyl, alpha beta unsaturated carbonyl, or beta keto carbonyl, beta acyl carbonyl. Those are all possibilities, and now we can hybridize all of the different carbonyl groups. So I gave you some tips on how to retrosynthesize the beta hydroxy carbonyl. Can you tell me what I can analyze about the product that informs me about the starting material? Say that again?
The group on the bottom. I reckon that the group has to only be on one of them, or it is on.
Needs to be two of the same thing.
Not necessarily, but there need to be two carbonyls. The starting materials must have two carbonyls. We're calling these crossed because they aren't the same carbonyl. Does that make sense? If it were just pure aldol condensation, then it would be two of the same carbonyl. So I need to have two carbonyls. I already have one. Where is the other? The beta carbon is the carbonyl carbon of the other reagent. The other equivalence, we were calling it on Tuesday. So you need to cleave the alpha beta bond. When you draw the starting materials, you cannot have that alpha beta bond. That is what's formed in this process. Here's a good tip. Redraw the entire structure. Exaggerate that alpha beta bond a little bit. And then erase that alpha beta bond. Now you've got your two components, but they're not quite in the right form because the alpha hydrogen was deprotonated to become a nucleophile, and that ended up over on the oxygen, and the oxygen needed to be part of a carbonyl. You guys were saying this, the beta carbon, I think you were saying this, the beta carbon is the carbonyl carbon. So you cleave alpha beta. Beta is now a carbonyl carbon, and we need to get there by alpha attacking it. That's the retrosynthesis. If you were to try and show this as a synthetic step, do I need to use LDA? I guess what I should say is, can I mix these two reagents together with one reagent and get this product? Or should I take one of them, react it with LDA first, and then introduce the other? The LDA first method is foolproof because it makes sure you don't have any mixtures. But some of our other methods for cross reactions were limit the number of alpha hydrogens, which limits the nucleophiles that can form. Benzaldehyde, no alpha hydrogens, cannot be a nucleophile. That means that the ester will be the only reagent that forms a nucleophile. Our second trick was promote selective reactivity. What is a more reactive carbonyl? Think back to Unit 4. Is the ester more electrophilic, or is the aldehyde more electrophilic? The aldehyde is more electrophilic. So you could do this as one step. You have only one nucleophile possible, and your electrophile is the better of the two electrophiles. So this would be a major product. You could answer this by saying MEO minus. Why MEO minus? It matches the ester linkage. But you could also, let me just redraw it as a whole separate set. And this would be foolproof. And again, you could show it as one step. You could take this ester and you could react it first with LDA. That makes sure that it cannot react with itself. And then you introduce the electrophile.
Could you have the functional group on the other one and do LDA that way?
So first of all, benzaldehyde won't react with LDA. There's no acidic hydrogen, no alpha hydrogen.
Swap the functional isopropyl?
The isopropyl group down here is connected to the alpha carbon of the ester.
Does it have to be the ester? Could it be that?
I think what you're asking was, could I break this so that I have this ketone and this methyl formate, formic acid, ants, formate? No. If you have these reagents, and let's say you use that same base, methoxide, what do you get? Are there any acidic hydrogens in either of these compounds? Are there any alpha hydrogens? Here? There is an alpha hydrogen here. There are no alpha hydrogens here. Okay, so let me draw the enolate that forms. This alpha hydrogen gets deprotonated, and now it attacks the ester, but the ester has a good leaving group. Think Claisen condensation. So the ester can kick off that good leaving group and reform a carbonyl with its other leaving group still on it, which is an aldehyde. So if you try to switch where that isopropyl group is connected, you get a beta acyl carbonyl rather than a beta hydroxy carbonyl. So it is significant how you break the bond. For reference, Killian, you were saying let's not cut this alpha beta bond. Even though we agreed beta hydroxy carbon is a carbonyl carbon. That's the only way it can become hydroxy. You suggested let's count from this carbonyl carbon, make this alpha and this position beta, and we cleave this side. It gives an entirely different product. Do you see what I'm saying?
Question. Going back to like what reagent?
Actually, I want to hear your question. I think I want to summarize what I just said again, though,
Okay.
and a little bit differently. Regardless of what your nucleophile is, when the aldehyde or ketone is the electrophile, you get beta hydroxy, aldol addition, or alpha beta unsaturated, aldol condensation. Regardless of what your nucleophile is, when your electrophile is an ester, you get beta acyl carbonyl. So these crossed condensations, it doesn't matter what the nucleophile is. The product is based on the electrophile. Functional group of the product is determined by the electrophile. All right, Jordan, whenever you're ready.
I was just gonna go back to like, I know you said for like base you had to use MEO minus. My question was like, also the condensation happening, why couldn't you use MEOH?
Because there's an ester in either one of these reactions, if we use NaOH in these reactions, we will saponify the ester. We will hydrolyze the ester. So anytime there's an ester involved, NaOH cannot be involved. It's actually safer to just always use, it's safer to always use an alkoxide that matches the ester linkage. Even if there is no ester linkage, well, I guess that's confusing, then it would just always be safer to use an alkoxide than ever using hydroxide. Or, as we discussed, use LDA. Whatever you want to make your nucleophile, react it with LDA. and then introduce whatever you want to be the electrophile. It is the electrophile that determines the functional group of the product. And I'm sorry I cut you off earlier. That's actually the first time I've ever gotten that put into words. All right. Questions on that problem? Do you understand our little side quest with trying to see if we had flipped the roles, if we had flipped the structures a bit, how things would have changed? Let's go to the next one. Really? What is the functional group formed here?
Beta ketoester.
Beta keto ester. Not quite.
Oh, beta keto ketone.
Beta keto ketone. Or in other words, beta acyl carbonyl. Okay, so based on what I was finally able to just identify, it doesn't matter the nucleophile, but this type of functional group can only be formed by a specific type of electrophile. What is the electrophile that helps us form a beta acyl carbonyl? Think about the last time we formed a beta acyl carbonyl. The electrophile was the ester. When an ester accepts electrons, it has a leaving group that it can kick off, so you get to preserve the carbonyl. Esters get attacked, kick off a group, carbonyl stays. So what we have to decide here is which, the alpha carbon must have attacked one of the carbonyls. We have to decide which we have to decide which carbonyl the alpha carbon belongs to. Do you guys agree that this is the alpha carbon in question, but whether this is the beta keto ketone or whether this is the beta keto ketone is up for grabs? We don't know. So let's explore both options. Let's say that this is my ketone, and this is the beta carbon that it attacked. So my green beta needs to have been an ester. When I retrosynthesize this, once again, I'm just going to redraw the starting material. And I'm going to cleave the alpha-beta bond that I made. Here's my carbonyl, here's alpha, here's beta. I'm going to cleave that alpha-beta bond. Beta, the electrophile carbon, has to be an ester. I'm really tight on space, so this is going to look a little ugly. Do you want it to be a methyl ester, an ethyl ester, a phenyl ester? Doesn't matter. Okay, so that's a weird conformation, but what that's really saying is one carbon on the chain, which was alpha to the ketone, went around and attacked an ester somewhere else on that chain. Let me draw this structure as a linear chain. Ketone, 1, 2, 3, 4, 5, 6. Ketone, 1, 2, 3, 4, 5, 6. And 6 was my carbonyl carbon. Keep in mind carbon 5 has this methyl group coming off of it. I identified it a carbonyl, That's going to be the nucleophilic position. Its alpha carbon is the one that attacks. The beta carbon that it attacks needs to have been an ester, so that when beta gets attacked, it kicks off its leaving group. Ketone, alpha, alpha will attack this beta. We formed a ring. That is a Deichmann reaction, or similar, where I do an intramolecular Claisen condensation to form a beta keto ketone. Let's cleave it the other way now. Let's identify this carbonyl as the nucleophilic carbonyl, which means its alpha position attacks this beta carbon. Once again, I can just redraw my starting materials. And erase the alpha-beta bond, because that is the goal that I'm trying to make in this reaction. Do you see that we broke a different bond this time? Because we called beta something different. Here, beta was on the right of alpha. Now, beta is on the left of alpha. I'm cleaving a different bond. And the beta that is attacked must be an ester. So I add in an ester group. Do you want it to be methyl? Do you want it to be ethyl? In this case, it doesn't matter, because I'm predicting an ester that it could have started from. So once again, this time, I have an ester being attacked by a ketone. Alpha of this carbon attacks this as beta. Are either of them impossible? Does either of them work better?
Chain seems pretty unlikely because they're so far apart.
Actually, the fact that they're on the same chain means they're closer than ever. These molecules could be separated by billions of solvent molecules. These are attached by 5 carbons. These are wiggly. They're like spaghetti strings. They're like shoelaces. You guys ever seen somebody that takes a rope and throws it in the air and ties a knot in the air? That's a little bit about like how reactions happen with intramolecular reactions. They just fold in on themselves and react with the right energy. So it actually is a lot easier for that intramolecular reaction. But let's think about the feasibility of the nucleophiles. Would you agree that this molecule has 3 alpha positions? Tertiary alpha to a ketone, secondary alpha to a ketone, and tertiary alpha to an ester. We know that esters are less acidic. Ester alpha positions are less acidic. So the ketone would be more likely to be deprotonated. But tertiary is more acidic than secondary. So what would I need to do in order to make sure that I deprotonate the secondary position and not the tertiary position? I can't add hydroxide because that would prefer the more substituted and hydrolyze the ester. I can't do tert butoxide because that would do transesterification on the ester. But I could do LDA because LDA would also prefer this position, the least substituted position, and then I would be able to attack the ester. So LDA with this reagent works great. And then it reacts with itself. In my second option, they're not connected to the same molecule, so I'm definitely able to do a first then second. But if I use LDA, does my nucleophile form the enolate at the correct position? Does LDA prefer to eliminate from this less substituted secondary carbon or the more substituted tertiary carbon?
The less substituted one.
LDA is big and bulky. It wants to go to whatever hydrogen is most accessible. That's the position I want it to attack from. So if I used something like hydroxide or ethoxide and I went to this more substituted position, I'd get a different product. This one also works well when I add first LDA and second my ester. We've got one retrosynthesis left. What is the product that we see?
Ester molecule.
Are you guys all right with me abbreviating those groups as TBU? Stands for what? Tert-butyl. And I'm sorry, did you say the functional group?
It's ester.
There's an ester.
What is it called? What LEA does?
Deprotonate. Complete enolization. Which one?
Both.
Good. Those are both true. Can you be more specific about the functional group? Remember, in this unit, Unit 5, we're doing the alpha substitution and alpha condensation reactions. I introduced new functional groups at the beginning because they are crucial to interpreting the condensation and addition reactions. So I don't want you to look at this and just say ester. Just like I don't want you to look at this and say a diketone. I want you to tell me as much information about that ester as you can.
Ester with an alpha alkene.
Ester with an alpha alkene.
Fully substituted.
Not fully substituted.
No hydrogen?
I see. I'm sorry. It is a tetra-substituted alkene. I thought you were saying saturated. That's my fault. Alpha beta unsaturated carbonyl. In this case, the carbonyl is an ester, but it's an alpha beta unsaturated carbonyl, also called a conjugated carbonyl. Can't just give it to you. Need to make you think about it. What reaction did we learn produced alpha beta unsaturated carbonyls?
Condensation.
Aldol condensation. Not Claisen condensation, which is what gives us the beta acyl carbonyl, because there you're reacting with an ester electrophile. Here we're doing aldol condensation. What is our electrophile on the aldol condensation?
Alpha hydrogen?
What carbonyl, what type of carbonyl is the electrophile when our ester beta is not a type of carbonyl. When our ester is the electrophile, we get this Claisen type condensation, beta keto carbonyl. The aldol addition and the aldol condensation have the same electrophile, aldehydes or ketones. I know there's an ester that's going to be in this reaction. Given the fact that the ester is still showing, the ester is the nucleophile. The only way to form a conjugated carbonyl is when the ketone or aldehyde is the electrophile. So here's alpha, here's beta. That's the bond I'm going to try and make. So when I retrosynthesize this, what am I going to do? Redraw the starting material, exaggerate that alpha-beta double bond, and do what? Cut it. Erase it. What do I do from here? Put a ketone on alpha or on beta? Good. Alpha carbon becomes the nucleophile and attacks beta. Look at that. Our beta carbon, our electrophile, was a ketone. That's the only way you can get to the conjugated carbonyl. Couldn't be an ester. Those are our structures. What might be a good way to run this reaction? NaOH will hydrolyze the ester. H3O plus will hydrolyze the ester. H3O plus works really well if you have a pure aldol condensation. If you have a ketone with itself doing the condensation. But for crossed reactions, H3O plus would not be great, especially since here H3O plus would hydrolyze. What's your foolproof method? LDA with the nucleophile followed by the electrophile. So we would write that as first LDA, second ditert butyl ketone.
Can't you do NaOET?
NaOET would facilitate the ester doing Claisen condensation with itself. Remember, we have methods of trying to minimize the byproduct of cross reactions. If I had both of these together at the same time, and I added NaOET, this cannot be a nucleophile. There are no alpha hydrogens. So this will be the only nucleophile created. But have I promoted selective reactivity as an electrophile? Well, ketones are more electrophilic than esters. But this ketone is highly sterically strained. It's got those diterbutyl groups kind of blocking its carbonyl position. So in order to minimize cross reactions, this would be the best way. Ethoxide would be a good alternative. I want to show you guys a little bit of how some of this shows up in multi-step synthesis, because you don't always need to show that you make an enolate with LDA. So let's say that we were given this problem a little bit differently. Let's say we had tert butoxide. Nope, I'm sorry. Let's say we had ditert butyl ketone, and we knew that we wanted to get to this final product. You guys are getting familiar now with saying 1 LDA, 2 second reagent. The problem is LDA doesn't react with this chemical. I don't want LDA with my electrophile. I want to use LDA with my nucleophile. What I want is a nucleophile with this alpha carbon to attack the carbonyl that I already have. That is as easy as saying, give me that nucleophile. Give me that alpha carbon with a negative charge. Done. You don't have to show how you made it. We know you used LDA. How do we know? I guess right now we've just agreed upon it. That's the only way to make that. Complete enolization. Here's an alternative though, if you're not comfortable with that. You could say, I want this ester and I want it to react with LDA. In that way, what you're saying is, I'm going to go into the lab, and to a beaker with diterbutyl ketone, I'm going to mix a beaker with this ester and LDA sitting together. But if you have these two sitting together, no, you don't. If these are together, this is what you have. Fair enough? What questions can I help answer on this? Thank you. It doesn't matter. It usually takes me 3 or 4 times to get it.
Could you name the product groups again?
Yes, actually, can you guys name the product groups? There are 3 main functional groups. Once you name them, I'll put them on the board.
So I think that one
You're welcome.
is this one.
I'll give you a hint. The 3 problems we just did correspond with the 3 problems.
Unsaturated
Correspond with the 3 functional groups that I want you to know.
carbonyl.
What are the 3 functional groups that form in these addition and condensation reactions? The new functional groups that form. What's one of them?
Alpha beta unsaturated.
Good. Alpha beta unsaturated carbonyl. This has an aldehyde or a ketone as the electrophile. Electrophile means what? Loves electrons, takes electrons, not the enolate. What's another functional group? Beta hydroxycarbonyl. What is the electrophile? I'll give you a hint. It's either aldehyde and ketone or ester. Is it ester?
Yeah, it's an ester.
No.
What?
This also has aldehyde or ketone as the electrophile, regardless of what the nucleophile was. What's the last one? Beta acyl carbonyl.
What does that mean?
Acyl means what?
Carbon group?
Not carbon group.
Carbon.
Carbonyl group. Acyl means carbonyl group. So what we're saying is, relative to a carbonyl, there's a carbonyl at the beta position.
Why is the middle one not an ester? Why do you not call it an ester?
You can only get a beta hydroxycarbonyl by aldol addition. That is when a nucleophile attacks an aldehyde and turns it into an alcohol, or a ketone and turns it into an alcohol. Aldehydes and ketones have no good leaving group. Esters, on the other hand, Esters have a leaving group. It's their OR group. And so esters can kick off an OR and preserve their carbonyl, which means that you're left with 2 carbonyls, regardless of what the nucleophile is. Ester nucleophile attacks ester. Aldehyde nucleophile attacks ester. Ketone nucleophile attacks ester. The functional group is all dependent on the electrophile that's attacked. All right. Good work. We have 1.5 new reactions to learn. I have some multi-step synthesis for us to do and 2 mechanisms to go through. The aldol condensation, which envelops the aldol addition, kind of like how the acetal formation mechanism enveloped the hemiacetal mechanism, and the Claisen condensation mechanism.
Question that came to mind. Since they say this is like carbonyl, is it saying that this can be done with like any carbonyl reaction? Like, or
No, not necessarily.
okay.
But that's a way of summarizing that the aldehyde could have been the one that attacked the ester, and so you could have a beta aldehyde, a beta ketone aldehyde, or even a beta ester aldehyde. Or the ketone could have been the carbonyl that attacked the ester, which means that you can have a beta aldehyde ketone, a beta keto ketone, or a beta ester ketone. Or an ester could have attacked an ester. So that carbonyl is not referring to amides or carboxylic acids. To an extent, decarboxylation reaction requires a beta carbonyl acid. So this can expand, but in the context of what we're talking about, these reactions, the carbonyls are only ever aldehydes, ketones, or esters. Especially if we made a beta acyl carbonyl and then used unit 4 reactions, hydrolyze an ester into a carboxylic acid, change that carboxylic acid into an amide, reduce the amide into an amine. You could do a synthetic pathway with reactions starting from here and going into carbonyl chemistry. Okay, where should I erase? Are you guys good? Better with this right side being erased? Our last mechanism, our last reaction and a half, I have shown in this 3-way diagram. Can you tell me the starting material here? You don't have to give me the name, although I know you can. I want you to give me the functional group. Alpha beta unsaturated carbonyl. Which means you guys know how to make that. Find alpha, find beta, cleave them. You're done. Well, you're not done. Beta needs to be a carbonyl. You know how to make this carbonyl. Now we're going to use it. Reaction number 1. Cuprates. Oh, you forgot about them.
Is this the conjugate addition mentioned in Gilman?
Yes. Gilman. Cuprate. That's it. First, we introduce a cuprate reagent. R2CuLi. We can make R anything we want it to be. R could be methyl, isopropyl, vinyl, phenyl, benzyl, followed by an aqueous workup. And what we get is an addition reaction to the conjugate position. This reaction is called conjugate addition. we know that Grignards and organolithium reagents are very strong nucleophiles and deliver their electrons directly to the carbonyl. Cuprates, on the other hand, attack at the conjugate position. So let's say that we have this R- group. I'm just dissociating it from the copper. When this R- group, no, I think I'll show it a little different. I will show that it is connected to the copper. When this R group takes electrons from copper, it shares it with the beta position, which means the beta position now has too many electrons and needs to get rid of some. So the alpha-beta unsaturated bond moves between alpha and the carbonyl carbon, and the carbonyl carbon gives electrons back to the oxygen. So we get this intermediate. R has now connected to the beta position, and I have an enolate. Cuprates are mild nucleophiles. They're not strong. The reason the cuprate prefers to attack here is because there's resonance in this molecule. This is a resonance stabilized product that makes it easier to form, more stable. Cuprates prefer to attack at the conjugate position and do conjugate addition. Cuprates are not the only reagent that like to do conjugate addition. When your conjugate addition is a nucleophile, this is acetaldehyde's enolate. I'm gonna make one change though, sorry. And that is, we don't have to introduce this as the enolate. Sometimes we introduce this with a base. And we know that this base creates an enolate at the alpha position, which means that in all essence, what we're adding is this guy. Now my nucleophile is the enolate, and the enolate is also a moderate nucleophile. The enolate is not a strong nucleophile. So the enolate also attacks at the beta position. Here's my carbonyl, my alpha-beta position. Now my beta carbon is also bonded to this nucleophilic alpha. I'm going to do some mapping so that you can tell what is what. Here's my conjugated carbonyl. Here's my conjugated carbonyl. Here's my nucleophilic enolate. And here's my nucleophilic enolate. That is a bit of an odd conformation for the molecule. We could write that as a linear chain, but that works. What would you call that functional group? I think you came up with the name for this one last time. That would be a good answer, but it can be really hard to find it. a shared beta dicarbonyl. Both of those carbonyls now have a shared beta position. This reaction is called the Michael addition. And I may have come up with a bad example of it because the last reaction we're going to see actually follows a Michael addition, and I think this Michael addition would do the same. Here's our last reaction. You can see that I'm saying that it's going to go up. And I think I'll explain why I gave a bad example to the right in a second. Instead of acetaldehyde, let's use acetone and hydroxide. You'll notice that I've noted on the paper, this is not isolated. We're going to form a very similar structure. In fact, you could copy the structure you have here and just add a methyl group off of the aldehyde carbonyl. We are still in the presence of that catalytic base, which means right now that hydroxide can actually continue reacting. And if that hydroxide reacts, it can form a reaction that loops in on itself and does an intramolecular aldol condensation. That would be where this alpha carbon on either side attacks this beta carbon, 1, 2, 3, 4, 5, 6 membered ring. Michael addition, followed by intramolecular aldol condensation, is called Robinson annulation. You can't make this shit up. They stole it from him. That's literally just a Michael addition. And then it reacts with itself. And they decided to name it after Robinson.
What's an annulation?
Do any of you know the word annulation outside of Robinson annulation, which you now know?
I'm guessing it's annulling.
I think it's...
I think it's more about yeah, but it's more like putting things together.
Oh, I thought annealing was not putting together, but removing. Isn't annealing like a purification process? Kayla's got an interesting idea that maybe it means annual, meaning cyclic, but I think that doesn't have two ends. Annulation has something to do with rings. Cameron, I'm sorry, I uploaded it now. So for the rest of the sheet, you'll be able to download it. So annulation means ring forming, but I don't really have a good way of connecting that for you. I don't think it's actually related to annual. I don't think it's related to nullification. I'm not sure.
Annuling's like when you reform something. That's why I thought that kind of makes sense.
Could be. If you want to look into it.
Metal, you heat it and then you reshape it.
Oh, okay.
It's like, I don't know.
It has something to do with the
branch of
fact that it
science.
forms a ring.
Yeah.
I know that much.
So that middle step is an intermediate?
It is an intermediate, which continues to react with the reagent. All right, here's why the reaction that I gave you was bad. The Michael addition to the right was a bad Michael addition because this alpha position is still in a place where it can attack the other beta position, which means the product I gave you here also does Robinson annulation. It's a bit of a different product. You'll notice that up here, the ketone has the alkene has a methyl coming off, and here the alkene does not have that methyl because we use different enolates during the Michael addition step. So I'm going to try and make this clear. Robinson annulation equals Michael addition followed by intramolecular Aldol condensation. Terrible. That guy got off easy.
What if it's the last name of Michael?
I think Michael is the last name, actually. Michael Robinson. You know what? If that is, I'll give it to him. Lucky guy. He actually gets both of his names on different reactions. Those are all of the reactions that I have for you this semester. Congratulations. You have come to the end of OChem 2. We're just not done yet. We have mechanisms for aldol condensation and Claisen condensation. And that's how I want to spend the second half of the time that we have, as well as doing multi-step synthesis, which of course is really challenging in this unit because of how obscure the functional groups look in the products that we form. So this is a challenging section. This is a challenging exercise. Why don't we take a 5-minute break? Come in here around 6:05, 6:06, and we'll start with, I want to start with mechanisms so we get them done, and we can work on multi-step synthesis when those are over.
Where does oxygen go in the annulation?
Leaves as water,
As HOO
which is the condensation product.
is
It condenses water out of the molecule.
as O2H.
No. Oh,
Where is it? Where is it?
boy.
Is that even possible?
Yeah. But without a charge, it's going to be scary.
Double bind to the hydrogen.
It'd be the radical that forms from hydrogen peroxide, except rather than where it normally forms between O and O, it would have to have the hydrogen split off as a radical. This is O2H. That's scary. Like you don't want to run into that guy. This might be so unstable that you'd actually just find atomic oxygen and hydroxide radical.
Where does it go? What is that? Are you losing a hydrogen too?
2 hydrogens go from CH3 to CH2. I'm sorry. Go from CH3 to CH. I know how to count.
You lose
No, you lose.
these 2 hydrogens.
Yeah, I mean, it's a symmetric molecule, so you can lose whoever you want. Keep this. Oh, all right. I felt like that was the easiest to copy down.
Not all students can get OChem as easy as you did.
Sorry about that. Saw you whip out that tool. Oh, it's okay. I was like, shoot, he's He's putting in the effort.
I can always say that. If I have nothing else, I'll go with that.
You said one of these couldn't be an ester.
The top two don't form by ester carbonyls. They can have ester nucleophiles, but that's what we were talking about. It doesn't matter what the nucleophile is, whether it be aldehyde, ketone, or ester. So this is what I would like the scientific community to come to a consensus on, among other things. Can we just call Aldol reactions the reactions where aldehydes and ketones are the electrophile? Because it gets really confusing with all the other combinations that are unnamed.
So is it wrong when we're discouraged to call these esters because there's
No, not at all. But I do want you to be able to recognize that it doesn't have to be an ester. It's the fact that it's a conjugated carbonyl that makes it significant.
This is the electrophile?
That's right. At the very least, we want to make that the electrophile.
Approximately 13.
Did you play the block game in high school?
Of course.
Did it really? Minecraft came out in 2010?
That's right.
2000s.
Oh,
It was more it got really more mainstream in 2013, I think.
Oh,
November 18th, 2011.
oh
Probably a
it was
beta
older.
version when it came out in 2012.
Oh, yeah.
Best selling video game of all time.
We got internet at my house in 2010. Really? I thought it was younger than that.
That's when I was in high school.
Yeah, me too. I must have just been more sheltered than you guys. I swear I never heard of Minecraft until
The free demo.
I feel like more recently than not. 2010 was 15 years, almost 16 years ago. That'll make you sick.
I hate time.
You can't have a ketone? Hey,
That's a ketone.
that's a ketone
Yeah.
and an ester.
No, that's not an ester. Ester needs to have two O's.
Look, it's an ester.
Ester nucleophile,
The map is map.
and it says it must have.
This is the
Hey.
electrophile.
I have 2 clocks in my room
Definitely not.
because
Alpha carbon is always the nucleophilic carbon.
Your massage thing, time
The beta one attacks?
now.
charge
No, I just said alpha is nucleophile. Nucleophile is negative charge. That's why electrophile says positive. Electrophile takes electrons. Nucleophile donates. I mean, you're in good company. I think half of us are like the same age.
So I would go back to
Sims. Roller Coaster Tycoon.
oh man, shoot.
Yeah.
I can still sit down
Maybe it'll
and
work
play
for you.
some roller coaster.
But then I'm just like,
Make a roller coaster that shoots off into nowhere.
you're not
I did that a few too many times. We get a part that's just full of vomit all over the place.
They put Roller Coaster Tycoon on the iPad now, so you can play it in a whole new generation.
Do you have to pay for it?
It's in the Apple Arcade, so if you have that, it's free.
Oh, okay.
Quote unquote free.
Oh, man. All right, let's do some mechanisms. So, I didn't clarify this on the reaction, but how many equivalences of my starting material are needed to get to my final product here?
2.
2. Even if it's not explicitly stated, you don't need to say 2. You're just taking half of what's there and reacting it with the other half of what's there. So this is the hard part. In general chemistry, we're like, balance, balance, balance your equations. And then we get to OChem and it's like, there's a billion of them. Who cares? So that is a challenge. I want you to be aware of it. If you want to, go ahead and add that 2x in front because that can be helpful. What might be a good base to facilitate this reaction?
Anything.
Not anything.
Why?
LDA would not be good. NaOH would be okay. What is the difference here between LDA and NaOH in facilitating this aldol condensation?
Oh. The LDA will want to go to the right carbon.
Less substituted, which means LDA would give me a structural isomer. I need a small base. So sodium hydroxide is a great option for us here. Or sodium methoxide, sodium F oxide. All right, first step, formation of the nucleophile. Formation of the enolate. Here's the deal. I'm going to keep 2 equivalences drawn in for each of the steps, even if that second equivalence is not involved. Does it matter which equivalence I attack first? No. In the past, I have asked students to show all resonance forms of their enolate. I think I'm diverging from that. In fact, after this semester, I think I may change how I ask most resonance form problems. I may ask that you only show the most stable resonance form, the major resonance form, which means in this case, hydroxide acts as a base to the alpha hydrogen. CH takes the electrons all the way up to the oxygen. Man, I don't like how I labeled it. I labeled step 2 as nucleophilic attack. I wish I had labeled it differently. If you want to rename this as acyl addition. How many times have we seen acyl addition this semester? A lot. Since Unit 3, we've been doing acyl addition. That's a little bit better than nucleophilic attack. Acyl addition requires a nucleophilic attack anyways. So, now that I have my enolate, the nucleophilic attack comes from the most reactive position. That's the alpha carbon. So my carbonyl reforms from O minus. The alpha carbon attacks the carbonyl carbon. And the CO bond breaks open.
Do you need the other molecule to be there for the oxygen to push the charge off of itself?
This is in resonance all the time. This is always in resonance with this form. Neither one exists. That lone pair and that negative charge is located across oxygen and the alpha carbon at the same time. When oxygen has it, it's more stable. When carbon has it, it's more reactive. So, to be fair, you could draw this and only this resonance form. That's perfectly legal, but this is the more stable resonance form. This is the more reactive resonance form. What you see in this second step is that the alpha carbon is reacting. That's what's happening here. The alpha carbon takes the electrons to do the nucleophilic attack. All right, now we get this kind of awkward, cumbersome little situation where we've got this O minus from this nucleophilic attack, and our two carbon chains have now fused. I'm drawing it this way because it kind of models the way that the structure is shown up above. But this is just one conformation. You can also draw this structure like this, if that's more helpful. I don't know. Sometimes it's nice to know there's more than one way. Sometimes it's a little annoying. Step 3, protonation. What's my acid? Water. Water is the conjugate acid of my base, hydroxide. By the way, if you're going through this and you're struggling to keep track of the carbons, what's a good way to map your carbons here? Label the carbonyl and alpha and beta. Label the carbonyl and alpha and beta. It's a good way to keep track because that's the skill we were using in the synthesis and the retrosynthesis. My alkoxide deprotonates water. What functional group have I just formed? Ooh, can you be more specific? It is a tertiary alcohol. Can you be more specific? Not just what bond was formed in making a functional group. What functional group is in this molecule? A beta hydroxy ketone. So if you said alcohol, if you said ketone, you're not wrong. But the specific relationship between them is important. This is the product of what reaction?
Aldol addition. Aldol addition.
I mean, you're not wrong. This is an acyl addition, specifically where the nucleophile is an enolate, which means this is
Aldol addition.
aldol addition. Congratulations, you've just learned the mechanism for aldol addition. Why stop there? Step 4. This new beta hydroxy carbonyl, I forgot to show this, sorry, up above. I also reform my catalyst. My new beta hydroxy carbonyl is in the presence of hydroxide. So I can do this again. I'm going to draw in the remaining alpha hydrogen. Ooh. I know it really blends in, so I want you to notice it. That's my second alpha hydrogen. And hydroxide acts as a base. And I reform my enolate. Just like last time, the CH bond becomes a CC double bond, and the CO double bond moves to O minus. Here I get water. That is the water that condenses out. That's my condensation product. The last step in my mechanism. Yes, Billy?
Is that H the most acidic?
It is the most acidic. Why?
Tell you.
Anybody else want to tell me why that H is the most acidic H? Oh, okay. Sorry. No, you have a valid point. What else might be more acidic? OH might be more acidic than the alpha hydrogen. So if OH gets deprotonated, would you agree that that is just reversing the last step? So doesn't actually show us anything new. But this OH has a pKa around 15 to 18, and this alpha hydrogen has a pKa around 17. So they're relatively in the same range of acidity because that alpha hydrogen is stabilized by the carbonyl. It's stabilized through resonance. My last step is elimination. I want you to notice something. Catalytic hydroxide, consumed, regenerated, consumed, and forms water as a byproduct. Is it a catalyst? No. And yet I told you that this is a base catalyzed reaction. I need to get hydroxide back. Where can I get hydroxide from in this molecule? I can kick off the alcohol, and I'll tell you something, this is the only reaction where you will kick off OH minus as a leaving group. Typically, that is a terrible leaving group, but we're in basic conditions, and I have just consumed my catalyst, and the catalyst needs to reform. CO double bond reforms. The CC pi bond shifts from carbonyl alpha to alpha beta, and the OH group leaves. Catalytic base reforms, and I have my alpha beta unsaturated carbonyl. I told you guys to use alpha and beta as markers, and then I kind of stopped showing them. So I'm gonna go back in and add those alpha betas so that you can see how those positions are involved at each step. Do you understand why I'm putting a dot? Yeah, I want you to have a reference point, but we don't have a name for it. We just call it carbonyl carbon. So I want you to be referenced at that carbonyl carbon that's involved in the enolate, and then map alpha and beta from there.
We wouldn't see it like that on the test because that would mean a radical, right? If you had a dot next to a carbon.
If you did, oh yeah.
Well, because when I first came in, I had missed the last few classes.
Sure.
And I hadn't seen that. I was like, that's weird.
That's a weird radical. Do you know what? If you showed me that dot on every position, I would not think it's a radical. I would think that you're mapping. In fact, if you showed me the dot and the alpha beta, I think I'd know because it's my method. But you have a really good point that that's dangerous.
I feel like there should be something more concrete for the carbonyl carbon because it's such a common reference point. But
Yep.
we just keep calling it the carbonyl carbon.
I know.
And
What do you have for me, Russ? What would you call it?
The North Star carbon.
Right. The North Star.
OG carbon.
The OG. I mean, really, it's a very versatile carbon because we know the carbonyl carbon can be electrophilic and accept electrons, and now we know the carbonyl carbon facilitates alpha hydrogen deprotonation by being involved in resonance. So maybe we label it as V, versatile. The versatile carbon, alpha and beta carbon. CC, okay,
What about
carbonyl
king-
carbon.
King carbon.
KC.
No, maybe.
I think then people are going to think it means ketone. All right, let's do our next one, which is the Claisen condensation. I gave you a beast of a molecule.
Wow.
Because I wanted to show you something fun.
Is that how the pharmacists make all those massively ringed drug structures?
I don't know. I'm not a pharmacist. But it could be. What reagent do I need to mix in here in order to get to this product?
MEO minus?
Sorry?
MEO minus?
MEO minus. Why? It needs to match the ester linkage. And we have two methyl esters. Is this technically a Claisen condensation or a Deichmann condensation?
This is a Deichmann condensation.
This is a Deichmann condensation because
They're connected.
it's intramolecular. They're connected. It forms a ring. All right. Do you remember something about the Claisen condensation and Deichmann condensation reactions? If you run this with a base, then the final product actually has a negative charge. So I added at the very end there, step 5, acid workup. So we're going to show this as first, my base, and second, acid workup. All right.
See if we could use HBO plus.
Oh, you're right. I did say try to use H+. And you and I had the conversation after class last week, right? You could use any aqueous acid so long as you kept it cold and you didn't bring it past pH 7. You don't want to make it acidic. You just want to neutralize the base. That is a great question, though. H+ looks better. All right, first step, formation of the enolate. That means identifying the alpha carbon. How many alpha hydrogens could I possibly eliminate from?
1. No, or 2, but on one molecule.
Okay, fair, good answer. There are 2 alpha hydrogens. It's at the same position. So I'm going to show one of those hydrogens and my base, MEO minus. And just like last time, I'm only going to show the major resonance form. You don't have to if you don't want to this time. But if you come take my class again, I might change my mind. Methoxide takes a hydrogen. CH bond becomes a CC bond. And the CO double bond breaks open. Formation of the enolate. My conjugate acid is methanol. Do you know what you get if you spell methanol backwards? Home. Because the methanol has to stay the same, so. Methyl alcohol. Home. It'll kill you though. Don't drink it. I told you guys that. Don't drink it. All right. Does that look different than our enolate from the aldol condensation? Can you tell me what's different? What's similar?
It looks
Okay.
O minus with an alkene right there.
O minus connected to an alkene. The only distinction here is I also have an OR group connected to that same position. Step 2. Once again, this might be a good place for you to change this. I called it nucleophilic attack, but a better name would be, louder, acyl addition, because that's what we're going to do. We're going to attack an acyl carbon. CO double bond reforms. Oxygen negative charge to a CO double bond. Alpha carbon attacks. Alpha carbon is taking the CC pi bond and it's attacking my electrophilic carbon. Somebody asked earlier, this being in the same ring, they seem so far away. Yeah, that's kind of a long arrow to draw, right? But remember that these bonds are wiggling and moving around and we're just waiting for them to run into each other. I need one more arrow. CO pi bond breaks open. All right, this means that we're going to form a ring. So this is a good place to map and make sure that you know how big your ring is going to be. Alpha attacks beta. That's alpha 1, 2, 3. That should be a 5-membered ring between alpha and beta. That also agrees with what our structure has above. So I have my benzene, and then I know I'm going to form a 5-membered ring from there. Take it slow at the start. Just draw that 5-membered ring. Now think about what's attached at your positions. This was 2 and 3. The benzene carbons, 2 and 3. Off of that was beta. Next to 2 was alpha. Alpha, oh, I forgot 1. Yeah, sorry. Alpha does not come after 2. 1 comes after 2. Alpha is up here at the top because I wanted to form an alpha-beta bond. Alpha-beta have now bonded, and they're connected by 1, 2, and 3. That's my way of mapping. If you don't want to use that way of mapping, that's okay. You could have called it alpha 2, 3, 4 beta. What's connected to alpha? Alpha also has an ester coming off of it. This is the ester that just reformed in that last step. What does beta have connected to it? Beta has an O- group and an OMe group. That's the product of our acyl addition.
Oh, why does it attack at the? Oh, it attacks at the bottom because there's no other. Because the other side is substituted.
There's no. This is the nucleophile.
The bottom.
Alpha.
Oh.
This is the electrophile. What's my next step? What am I going to eliminate? Oh, I want to take you back a step. I'm sorry. Remember this methanol? That's our condensation product. What happened in the first step? Which means I have not yet reformed my catalyst. Much like last time, what did I eliminate here? I eliminated OH minus. We'll do the same thing. Elimination CO negative becomes CO double bond. Kicks off OMe. OMe is a good leaving group here. That means I just reformed my carbonyl. Congratulations. You now have a beta acyl carbonyl. The problem is you just created a good base and an even more acidic alpha hydrogen. This is that part of the reaction that I told you guys I didn't quite understand when I was taking this class. So now I want to see if you all understand this aspect. Why are we about to undo the product we just worked to make? Because that's what happens. Life's not fair. Listen, if this whole first step was able to happen based on the acidity of the alpha hydrogen, then this next step definitely has to happen based on the acidity of the alpha hydrogen. There are 3 resonance forms that you can show. It doesn't matter which one you show. I'm going to show just the resonance form where it's stuck on the alpha carbon. You could show this going up to either of the carbonyls just like last time. I'm going to show it like this. That gives me methanol as well. Yes, sir.
In this reaction, it doesn't matter if you use methanol or not because,
Yes.
well, but it goes away in the first step.
Yeah, but I still have a methyl ester there. All right, step 5 is the point in lab where you have finished everything that you're doing, and then you go to the fume hood and you grab acid and you start adding that acid to your flask. This is the acid workup. You finished your reaction, now you want to get your product. So now we're going to introduce H+. And of course, our base here is that alpha carbon. Not a 6-member ring, is it? Killian asked an interesting question earlier. He said, is this how they make those big polycyclic drugs? I'll be honest, I'm not sure. And yeah.
Because when I was looking at my drug, it seems like a lot of the drugs that I looked up, they have like some kind of organic precursor, like in terms of like came from a plant. And
Yeah.
they just modify those, I mean, significantly, but not like, they're not forming those multi-cyclic rings. Those are coming from some kind of natural precursor, and then they're just getting modified relatively slightly.
Sure.
Ways.
Biology really does a good job at chemistry.
Yeah.
Biology
Almost everyone
mastered
is
these chemical reactions.
like that.
Sure.
Very few are like purely synthetic, especially not the really big ones.
Did I lose a carbon? I think I lost a carbon in this final structure. So I can't say for sure. Is that too many? 1, 2, 3, 4, 5. Oh, it was just a really ugly 5-membered ring. Okay, sorry. I can't say for sure, but I do know that these reactions can be used to create large, complex cyclic molecules. One thing that I like to do about some of these reactions, especially on your final exam, is I like to have a multiple choice section that relates to these types of questions. And it might say something like, which reagent is missing in this synthesis, and which of the intermediates shown below does not exist during the mechanism. And that kind of gives you a leg up when you have to do the mechanism, because you have a reference question to go through and look at possible structures that really should be in your mechanism when you're drawing it. Here's another cool thing I thought about with this one. Do you remember the beta keto ester can go through hydrolysis and decarboxylation? And this I thought would be a cute molecule. You got a 5-membered ring, bicyclic to a benzene ring with a ketone on it. Very nice. And I like to do those in the multi-step synthesis or the roadmap problems on your final as well. I like to have you build structures using reactions like oxidation of alcohols, elimination of alcohols, and then that allows you to create carbonyls that you can do acyl addition, aldol addition, aldol condensation with. That means that you can do Michael addition and Robinson annulation. Sometimes that means that you can end with something like this and do decarboxylation. There's so many fun ways that these reactions all feed into each other. So just know that these reactions will come in and they'll be mixed with other reactions. Just know that. Yeah, I don't know how much of a hint that is to you, but
I'll take even the smallest crumb.
all right. Now I recognize we have 9 minutes left. Do you have questions on the mechanism you want to ask before we move on? Did we show everything, by the way? Did we show that we didn't really show that our catalyst reformed. That's because our catalyst never did reform. It acted again as a base. In the last 9 minutes, I would love to have you guys try working on these multi-step synthesis problems, asking questions as you go, thinking about what you can do with the starting materials and how you can make those final products. I will tell you that these involve Michael addition in both of them, as well as some of the other condensation reactions. No, sorry, they both involve conjugate addition. And Michael is conjugate addition. That's what I wanted to clarify. There's a version of conjugate addition that is not Michael addition in one of these. I guess maybe I'll ask this. Do you want to spend 9 minutes going through this alone? Or do you want to have the thought process? Otherwise, I'll film a video tomorrow solving these, and I'll post that to Canvas and YouTube.
Or be like loosely scaffolded.
It is loosely scaffolded.
Well,
Very loose, like a thread.
that's where you're throwing out hints of like, all this stuff. Where's your alcohol?
What functional groups do you see in the final product?
Professor, if you protonate with HCl, that would work here, right? Use HCl.
Yeah. Mm-hmm.
Well, does the chlorine just leave as chlorine gas?
Chloride ion.
Will it make chlorine gas?
No, it would make chloride ion.
So you pour it in the beaker, and then someone boils the waste beaker, because what would it do?
It would probably precipitate a salt once all of the solvent has evaporated.
Is chloride salt?
Yeah, and whatever cation is balancing it.
Well, aren't chloride molecules?
No, not.
gas?
There is no chloride salt. Is that what you said?
Yeah.
Negative and negative don't come together.
So
there's a cation that's
wait a
balancing.
minute. There's extra.
Do you know what the cation is?
Oh.
How come I never showed
It's
sodium?
salt.
Because it's a spectator ion. Doesn't play a role in chemistry.
Always just disappears.
And my Ochem 1 students struggle with that. Yesterday I was teaching them about substitution and elimination, and I said, if you ever show me this, I will take a small number of points off because you're wrong.
Did you tell me that? And did you take off points? Yeah. I remember. I was there.
It took me a while to start ignoring NA. Not that ignoring, but you just kind of like, don't worry about it.
The other challenge that I have is in class, I don't always put NA. I just put the anion. But then on the homework and on the tests, then it has the cation. So they're like, I don't know what to do with this. Oh, ignore it. I even tell my Gen Chem students. So that's the thing. I'm trying to start them young. I tell my Gen Chem students, ignore the spectators. They're not doing chemistry.
Shoot. Okay, this is taking.
If you see similar functional groups in here, go back to the problems that we did that formed things like that, and think about what functional groups need to precursor them. I think that's a good word.
Oh, you could do this too? No, you can only do one.
That's one of the things that I struggle with when we get to some of these bigger molecules is, I'm just really focusing on the homework, when you see these longer chains, maybe that have phenol or a benzene attached to them, and you're trying to figure out which parts stay together and which ones come together. So here, we're starting with one ketone, writing
Mm.
we're just trying to figure out how we can glue in yours together.
Yeah.
Is that fair?
Yep. No, you're exactly right. And we're gluing everything together by means of deprotonating a carbon and having that attack another carbon. Either another carbonyl carbon or a conjugate carbon, conjugate addition.
And for a problem like this, which is kind of coming up with whatever that would be that gets us to the final product.
Exactly. So you do have to kind of be creative about molecules. Invent something,
But you have to invent it with alpha, beta
and it has to exist.
context.
There's some people that will invent a molecule that can't exist. For instance, put a Grignard on a molecule with a ketone. It doesn't exist because it will react with itself, right? So there's some creativity that has to go into it, and critical thinking in tandem. But once you see the patterns over and over again, then they become easier to recognize. I only have 2 minutes left, so I really don't think I can give you guys the answers here. So I'll record a solution to these problems, and I'll post that tomorrow morning so that you have time to review it. But I want to direct you somewhere in the event that you are like most students and you're struggling with some of these concepts. Come to the Canvas homepage, and not homepage, so the modules page on Canvas, and scroll down to the bottom where it says old 2320 study materials. Listen, it says old because it's old to me. These are my old homework assignments. I think I told you guys about this early on in the semester. At least I try to, but I overwhelm you guys on the first day with information. These are my old homework assignments, and towards the bottom, you will recognize that there's some stuff on amines, and we're not doing that. Here is a homework assignment on enols and enolates. That's this whole unit that we're doing right now. And there are more problems similar to what we're doing. Synthesis problems, retrosynthesis problems, some arrow pushing problems. So come down and find these worksheets. This big arrow means retrosynthesize. Tell me what this could be made from. And some of them have more than one correct answer. So take a shot at it, practice them, and then look at the answer key and gauge how close you were or see what track you kind of got off of. You've got a unit test that opens tomorrow morning. Tuesday, we have review all day. Thursday, review all day. So come with questions specific about active homework, unit tests, written work, general topics, or specific questions from the midterm, the practice final. Come with any questions you have, specific or general, and we'll answer them Tuesday and Thursday. And start on your cheat sheet. Start this weekend while you're doing the Unit 5 test. Start thinking about things you want to put on there, examples you want to have, so that next week you can revise it and have the strongest cheat sheet you can have for the final. All right, guys. It's been a great semester. Have a good night. See you next week. You look like a Catholic painting.